Hello everybody, my name is Mr. Fetu Kiruhanga. In today's session, we are going to discuss on the topic of electromagnetism and the subtopic of magnetic field. We are going to use the Biot-Savart Law to derive the expression for magnetic field along the axis of the circular coil. Biot-Savart Law states that the magnitude of magnetic field dB is proportional to steady current, the length of a small element dl, and the sine of the angle theta, and is inversely proportional to the square of the distance r. Now if you check here in this diagram, our small length is this one, dl, and when we say sine of theta, theta is the angle between the small length and the line which is joining the small length to point P, and r is the distance from the small length to point P where we are looking for magnetic field. Now the mathematical expression for Biot-Savart Law is this one: dB is proportional to I dl sine of theta over r square. If we take out the proportional sign, we are going to introduce a proportional constant, which is this one, mu naught over 4 pi. Now the equation for Biot-Savart Law is always written in this form, that is dB is equal to mu naught over 4 pi, which is the constant, we multiply by I dl sine of theta over r square. Therefore, in today's session, we are going to use the application of Biot-Savart Law to derive expression for magnetic field along the axis of the circular coil. And the expression which we are going to derive is this one. The expression which we are going to derive says that B is equal to mu naught I r square n over 2 open brackets x square plus r square close brackets raised to 3 over 2. I is the current, r is the radius of the coil, n is the number of turns, x is the distance from the center of the coil to point P, and the mu naught is the constant called permeability of free space. Now let us go to the derivation of this expression. We are going to see how we can derive this expression by using Biot-Savart Law. Therefore, in deriving the expression for magnetic field along any point on the axis of the circular coil, which is mu naught I r square n over 2 in brackets, we write r square minus x square in brackets raised to 3 over 2. This is the expression which we are supposed to derive. Now, in deriving this expression, first of all, we need to be able to draw the diagram, which we are going to use to derive this expression. In the diagram, we draw it in this way. we draw a circular coil here. This is our circular coil, and we have a small length here which we are going to consider in our derivation. We call it dl, and the radius of the circular coil, we call it r. This is the axis of the circular coil. Therefore, when we say along the axis, we mean this line. We want to get magnetic field at this point, we may call it P. And the line joining a small point to point P, draw a straight line, this one, yeah, like that. The distance from the center of the circular coil to point P, we call it X, sorry. We call it X, and the distance from the small length to point P along this line here, we call it A. Now, one of the things which you need to be able to note when you are drawing this diagram with that, the magnetic field will always act perpendicular to this line which is joining small length dl and the point P. Therefore, you are going to draw here the magnetic field perpendicular to that line, and this magnetic field you are going to call it dB according to Biot. This angle here we may call it alpha, which will be the same with this one, and this is perpendicular, therefore is 90 here. Now, if this angle is 90 and this angle is alpha, the remaining angle here will be 90 minus alpha. This will be the angle between the horizontal and the magnetic field here. Therefore, in this diagram, we need to resolve this magnetic field, because the magnetic field here is neither horizontal or vertical. Therefore, we are going to resolve the magnetic field into vertical and horizontal component. Remember, the angle we have written here is 90 minus alpha. That is the angle which will be used. Therefore, the vertical component here will be this one, and the horizontal component will be represented by this line here. We have the value of this angle, it's 90 minus alpha. Therefore, here the vertical component will be dB sine of 90 minus alpha. The horizontal component here is adjacent, will be dB cos of 90 minus alpha, like that. Therefore, this will be our component. We have two components. Now, let us call the vertical component, let us call it dBV. Vertical component, we call it dBV, which will be equal to dB sine of 90 minus alpha. And the horizontal component, let us call it dBH. Therefore, dBH will be equal to dB cos of 90 minus alpha. Those components we have obtained here. Now we need to note something from the diagram we're having. Let us draw something. Now assume this is the component at the upper part of the circular coil, but there is a component which is on the other side, which is opposite to that one at the upper. We draw it here. We call it also the yellow on the other side. Now we may draw a line which is joining the yellow and the point P like that. This is the line. We may call this A, and the dB will be here. This will be dB, will be dB, dB will be there, and dB will be resolved into two components. There is a vertical component acting downward here. We are going to call it dB sine, dB sine of 90 minus alpha, and then we have horizontal component which will be directed this direction. Call it dB cos of 90 minus alpha. Now in this diagram you may note something. Horizontal components are directed on the same direction, but vertical components are directed on the opposite direction. Therefore, since vertical components are opposite, we say they are going to cancel each other. They are going to cancel each other. Therefore, in this derivation, the only component you are going to use is the horizontal component. That is the important thing you need to note when you are deriving the expression of magnetic field along the axis of the circular coil by using Biot-Savart Law. Therefore, vertical components are going to cancel each other for every element on the circular coil, but horizontal components are going to add each other. Therefore, in our derivation, we are going to remain with horizontal component only. In our derivation, we are going to remain with horizontal component only. Now let us consider the horizontal component. As we have said, vertical component have cancelled each other. So let me lab this one, and I want to use the black pen. Vertical component is here, horizontal component is here. Here is cos of 90 minus alpha, something like that. Therefore, we are going to leave the vertical component. We are going to continue with the horizontal component. Now for horizontal component, let us write the expression for Biot-Savart. Now the Biot-Savart expression is written as dB is equal to, we said, mu naught over 4 pi, which is a constant. We multiply by I multiplied by dl times sine of theta. We divide by the distance between the small length and point P. Now that distance here is A. Therefore, we put here A square. We are going to take this expression of magnetic field. We are going to substitute it here. If we place it there, what you obtain is dB H. Now dB H will be equal, we write this expression there, naught over 4 pi, naught over 4 pi we multiply by I, dl sine of theta, we divide by a square, and we multiply by this expression here, cos of 90, we multiply by cos of 90, 90 minus alpha, just like that, we multiply by that thing. The line there. Now let us check how we can simplify, how we are going to simplify cos of 90 minus alpha. We say but we may write cos of 90 minus alpha can be written as cos of 90 cos of alpha, cos of 90 cos of alpha plus sine of 90 sine of alpha. We may expand that expression that way, but cos of 90 is equal to 0, therefore this term will reduce to 0, and the sine of 90 is equal to 1. Therefore what we are going to, the expression which is going to remain there, be cos of 90 minus alpha is equal to sine of alpha. Now we take this sine of alpha, we substitute here. The expression we are going to have is dBH is equal to dBH is equal to mu naught over 4 pi I multiply by dl sine theta over a square I multiply by sine of alpha. Now let us go to the diagram here. Sine of alpha, which is this one, will be equal to opposite, which is r, over hypotenuse, which is a. We may substitute it here. Therefore we say also sine of what? Sine of alpha is equal to r over a. Now we put this one here, we substitute it there, we're going to get dBH, which is the horizontal component, not the vertical component, mu naught over 4 pi we multiply by I dl sine of theta, we divide by a square, we multiply by r over a. We are going to get a square times a, we are going to get a cubed. Therefore expression we will use to dBH is equal to mu naught over 4 pi we multiply by I dl sine of theta over a cubed very cute. But here we multiply by R. We have R somewhere there. Now this is the expression for magnetic field. With the expression for magnetic field for the horizontal component of this element. Now if we consider all elements along the circular coil, means we need to find the summation of the horizontal component along the circular coil. And to get that summation means we are going to integrate this expression here. Therefore, let us integrate that equation here. This side here, dBH, we are going to integrate dBH with limits from 0 to B, which is the total magnetic field. Now let us take all the constants out so that simplify the calculations. Then 4 pi, I multiply by I R sine of theta, I divided by A cubed. Now I multiply by, I'm going to integrate now that small length dl, integrating dl from 0 to 2 pi r. Why have we integrated from 0 to 2 pi r? Because when you consider all small elements along the circular coil, you are going to get the circumference of that circular coil. That is why we are integrating from 0 to pi r. Now here we are going to get, if we are integrating this expression, we are going to get B will be equal to, here we are going to write mu naught I R sine of theta, we divide by 4 pi A cubed. Integrating here, we are going to get L with limits from 0 to 2 pi R. Now inserting the limits in our expression, we are going to get B is equal to mu naught I R sine of theta, then we divide by 4 pi A cubed. I multiply by 2 pi r. Therefore, pi and pi will cancel here, and this 2 here will cancel with this 4 here. We are going to get 2 here. The final expression will be B is equal to mu naught I R square, now be R square sine of theta, then we divide by 2 A cubed. Now the angle theta is 90. Angle theta is 90 because the line which is joining the small length dl and point P is tangent to that small length there. Therefore, we say the angle theta will be equal to 90 with that reason. So we say theta is equal to 90 degrees. If we substitute here, sine of theta will be equal to 1. sine of 90 will give us 1. Therefore here will be 1. The expression which is remaining is B is equal to mu naught I R square over 2A cubed. Therefore we have obtained this first expression for magnetic field along the axis of the circular coil. That is B is equal to mu naught I R square over 2A. Now let us continue to see how we are going to get the expression which we are required to derive. And from this expression here, let us check A here. Here the top is A, here the adjacent is X, and the opposite is Y. If you use Pythagoras theorem there, you may write A square is equal to R square plus by X square by Pythagoras theorem. Now if you take under root on both sides, you're going to get A is equal to R square plus X square in brackets, you close the bracket there, and then we write 3 over 2. Now this expression here, no, it's not 3 over 2, it's raised to 2. Raised to 2, I'm sorry. Here is raised to a half. It's raised to a half, because we have taken the square root on both sides. Therefore here it will be a half. Now we take this A, we substitute here on this expression there. Therefore we're going to get B is equal to mu naught I R square over 2 in brackets R square plus X square in brackets. We have cubed here, therefore that one will come there. 3 times a half is equal to 3 over 2. Now we say for any turns, this is expression for single turn of the circular coil. If you have many turns, we multiply this expression by n. Multiply that expression by n. Hence we have obtained the required expression for magnetic field along any point on the axis of the circular coil. Now we are going to check how we are going to reduce this expression to get the expression for magnetic field at the center of the circular coil, and also how are we going to use this expression to get the magnetic field for Helmholtz coil. Thank you for watching. Subscribe through our channel to receive more study material. Have a nice time.